Now we will derive the inverse kinematics of the RRR manipulator. So this is an three-way articulated arm manipulator with three revolute joints. So the inverse kinematic problem is that the position and orientation of the end point or the end effector, it is known to you. So that is the transformation matrix T, it is known to you. And you need to determine the joint angles, that is theta 1, theta 2 and theta 3. Theta 1, theta 2 and theta 3. All the three joint angles you need to determine. So this first step is that we need to get the forward kinematic model of the manipulator. So only from the forward kinematics we will derive the inverse kinematics model. So for deriving the forward kinematics, we are using the DH method. That is, first you just assign the frames and derive the DH table. So this is already done in forward kinematics, so I'll not go into details of it. I'll just skip this. So this is the forward kinematic model of the RRR manipulator. As you see here, the individual transformation matrices are obtained from each row of DH table, and then you just get the overall transformation matrix or the forward kinematic model. So this is what you get. So now you have the forward kinematic model with you, and also the position and the orientation of the end effector is also known with you. So now equating both. So this is your forward kinematic model, and this is the known position and orientation of the end effector. So as given in the guideline, always it is, instead of using the rotation information, it is always suggested that we have to use first the positional elements in order to just derive. So first we will just equate the corresponding components of the positional vectors. Let us use this R14 and R24. So you get R14 is equal to C1 L3 C23 plus L2 C2, and R24 is equal to S1 L3 C23 plus L2 C2. So when you just divide, you can just easily cancel out this term, and then it will be very easy to determine the theta 1. So how you do that? So here on equating both the elements, that is, you will be getting R14 equal to and R24 equal to this equations as given here. Now you divide equation 2 by 3, so that you will be getting sin theta 1 by cos theta 1 is equal to R24 by R14. So from that you can easily get the theta 1 angle, that is just nothing but the tan inverse of R24 comma R14, right? So now in order to just get the angles, remaining angle, that is theta 2 and theta 3. So in triple R manipulator, as I told you, have to find three angles, theta 1, theta 2 and theta 3. Now we have got theta 1 angle. So now remaining we have to just find theta 2 and theta 3. So in order to get that, we will be using the inverse transform approach. So how do you do that? So you have to post multiply the inverse of the transformation. So here T0, that T1 to 0, T2 to 1 will be equal to, so this is the known transformation. You have to post multiply the inverse of the transformation matrix, that is T3 to 2, right? So that is, we are using the inverse transform approach here. So we have already this uh, T3 to 2 transformation matrix that you have already. So just post multiplying that, sorry, first we have to get the inverse of it. So you have to get the inverse of it. So how do you get the inverse of any transformation matrix? So the rotation part, you just take the transpose. So this is the rotation part. So just take the transpose of it, so that you will be getting this, right? And how will you get the, for the positional component, you have to get the negative dot product of the that is as given here. You have to get the negative dot product of R3 to 2 and D 3 to 2, right? So that you'll be getting this, right? So now you just post multiply this matrix to the transformation, known transformation matrix. So that you will be getting this expression. Now from that you can just equating the positional vector components. You get three equations like as shown here, that is L2 C1 C2 equal to minus L3 R11 plus R14, and L2 S1 C2 is equal to minus L3 R21 plus R24, and L2 S2 is equal to minus L3 R31 plus R34. Right. So in order to solve for theta 2 and theta 3, we will just squaring and adding the fourth and fifth equation. So it will be getting L2 squared C1 squared C2 squared is equal to this term the whole square plus L2 on the left hand side L2 squared S1 squared C2 squared. So plus this term the whole square. So that is what you have here. So summing the left hand side and summing the right hand side, you will be getting this. So from this, you know, cos theta 1, cos square theta 1 plus sin square theta 1 is 1. So in left hand side, you will be getting L2 C2, and dividing equation 6 by 7. So here you have the equation 6 as L2 S2. So you just divide 6 by 7. So in the left hand side you will be getting sine in form sine by cos. Right. So sine theta 2 by cos theta 2. So from that you can get theta 2, which is tan inverse of this particular value. Tan inverse of this expression you can get. And now the remaining is that you need to get the third angle. So how you get it? So it is you can get first you get the theta 2 plus theta 3 you find, and if you know theta 2 you can easily get theta 3 from that. So you can, so from that yeah, after doing the inverse transform, so if you just divide the element 3 comma 1 and 3 comma 2, you will be getting as 2 3 by C23 is equal to R31 by R32. So this is tan theta 2 plus theta 3. So tan theta 2 plus theta 3 is equal to R31 by R32. So we'll be, if you know theta 2, you can get theta 3 by using this expression. Right. So this is how you just determine the three angles of your triple R manipulator if you are given the end effector